Which is the advantages of this big capacitance? As I told you, bigger capacitance means lower voltage increment. But there is also another advantages. If you think during the freewheeling, the charged inductance have been discharged, are discharged across the capacitance, but this current flows through the capacitor during the transitory. Bigger capacitance means bigger current flowing here. If the current flows here, means the current flows also through the load, which is the energy that we want to send. Our purpose is to send the maximum energy to the load, so maximizing the capacitors means maximizing also the current here. Is realized if you think this resistance is our load, so the electrode's output, you get a RC circuit in series, namely a low pass filter. So the raising edge is slower and more energy is transferred to the load. Another advantage is for the TVS diode. The TVS diode is played here. So if you reduce the voltage across the MOSFET, you reduce the voltage across the diode. So less energy is wasted through the TVS diode, and the diode is also saved from extra power dissipation. Here is shown the transitory during the turn off of the MOSFETs. The overvoltage due to the two lines is pretty high. This waveform is captured at 2 milliseconds per division. Zooming it, you can appreciate the length is about 150 microseconds, and the pulse reaches 21 volts, which is the breakdown of the TVS. But in the previous version, without the TVS, what happened? This voltage increased a lot. It reached the breakdown voltage of the MOSFETs, and the MOSFETs were close to damaging. They withstand with this extra voltage because they were oversized, but they never turn off, because when they were in breakdown, even if the control circuit forced them to be off, they still were in on position. So when I attached it to the strips, the current continued to flow through the strips, and I remember I risked to damage my batteries. So take care of it, put the more capacitance and more TVS available, because otherwise the MOSFET can fail. Let's go to the MOSFET's copper bar design. This is my rough design made up of some layers of copper bar. The construction here represented is created with the main purpose of replacing the MOSFET easily if they are damaged. If they are soldered over the board, you can only to throw off them. You cannot reuse the board. In this case, you can take off the screw and utilize it again. One feature is how to get a perfect connection between the MOSFETs and the copper bar. I placed between them a tinned copper shield. Tinned because I prevent the oxidation. A copper shield because the pattern entails a perfect current distribution between the contact of the MOSFET and the copper bar. So I put it behind the MOSFET here in this region where there is the drain and the source here where there are the leads. With some pressure the connection between the leads and the copper bar is perfect. More homogeneous current means better distribution of the power across each MOSFET. So there are no MOSFET overload and overall the performance is better. It's better to have less number of MOSFET instead of a lot of MOSFET but not well connected each other. This is the result of the copper bar construction inside the case. As you can see, there are the two Schottky diodes in parallel. The 9 ceramic capacitor with low ESR here. The 8 MOSFETs able to provide 557 amperes in continuous, so a very huge amount of current. And I used the 3 TBS diode in parallel. Each one is able to clamp 250 amps. So also them are oversized, but the cost is very low. I prefer to put 3 of them, even if just one is enough. So as I told you, the external part of the copper bar is the connection of the source of the MOSFET, while the drain is the inner part. The screws utilized here are electrical conductors. At the same time, they have a structural action over the bar. In this slide, I'm going to talk about the current transient capture, which is the current at the gate of the MOSFETs. This slide is got from my previous video regarding the birch board. As I told in the past, the birch board has a turn-off time of 0.1 milliseconds, which corresponds to in the safe operating area at this point. So you have the voltage during the load less than 10 volts with 0.5 milliseconds correspond to a current less than 200 amperes. So each MOSFET is able to provide 200 amperes instead of the design one. This means that a lot of heat is created, so many YouTubers put an heatsink here instead of replacing the driver part. In my case, I decided to use this integrated circuit which provides a lot of current, and as you can see from the driver out waveform, namely this point, before to arrive to the gates of the MOSFET, I have a very short rising edge. The turn on time is sharp. Taking the turn off time from this point, you can see the falling edge. Here the time span is about 1 microsecond, but if you take the same turn off time across the gate of the MOSFET, you have a less sharp voltage. If you think the turn on of the MOSFET is around 1.7 volts, you see that the turn off time is about 1 microsecond.